Deep beneath the surface of Mars, buried in rock layers dating back billions of years, robotic explorers have discovered something that defies explanation. Microscopic metallic spherules scattered across the red planet's ancient lakebeds in a pattern that mirrors exactly what we observe from modern industrial pollution on Earth. But these particles predate human civilization by an impossible margin. We have always assumed we were unique, the only intelligence to harness electricity, to forge steel, to split atoms, and fundamentally alter a planet's atmosphere through technology. But what if this assumption is completely wrong? What if Mars once hosted an advanced civilization, and the relentless march of geological time simply erased every obvious trace of their existence? Today, we embark on a journey through evidence that challenges our most fundamental beliefs about our neighboring world. We will examine vanished technological signatures, explore mysterious atmospheric anomalies, and investigate why Mars's geological record contains such staggering, unexplained gaps. We will confront the possibility that we may not be the first technological species in our solar system. Prepare yourself. Our investigation begins now. In 2004, the Mars Exploration Rover Opportunity was analyzing sedimentary rock formations in Meridiani Planum when its instruments detected something remarkable. A thin layer of rock marking a distinct geological boundary contained concentrations of osmium and platinum nearly 40 times higher than the surrounding strata. These rare metals are common in certain types of asteroids, but extraordinarily scarce in Martian crust. The discovery fundamentally altered our understanding of Mars's violent past. That precious metal spike became evidence of a catastrophic asteroid impact that may have triggered dramatic climate change on Mars approximately 3.7 billion years ago. But what captivated planetary scientists most was how distinctly this single catastrophic event registered in the geological record. This revelation sparked an unsettling question. If one asteroid impact could leave such unmistakable traces after billions of years, what signatures would an advanced technological civilization leave behind? And more critically, would we recognize them? The Martian Hypothesis emerged from this line of thinking. Named after our mysterious red neighbor, this scientific framework asks whether industrial civilizations could have existed on Mars long before humans evolved on Earth, leaving behind traces so subtle or so transformed by geological processes that we simply haven't recognized them yet. Consider the magnitude of deep time. If a Martian industrial civilization lasted just 20,000 years and then disappeared, that period would represent merely 0.0005% of Mars's 4.6 billion year history. Locating evidence of such a brief interval would be like searching for a specific paragraph in a library containing 10 million books. Yet evidence should exist. Every industrial civilization must consume energy, modify atmospheric chemistry, and generate waste products that persist far longer than structures or machinery. These signatures become embedded in a planet's permanent geological record, preserved in rock strata, polar ice deposits, and sediment layers. The difficulty lies in identifying these signatures. We understand what modern industrial activity looks like because we are creating it in real time. We release greenhouse gases into our atmosphere, distribute plastic microparticles across our biosphere, and produce radioactive isotopes that will endure for millennia. Future geologists would readily identify humanity's impact on Earth. But what if previous civilizations employed fundamentally different technologies? What if they harnessed energy sources we haven't yet discovered or developed materials that degrade along pathways unlike our plastics and concrete? Their industrial signatures might exist in plain view, misidentified as natural phenomena. The osmium layer demonstrates that Mars preserves evidence of dramatic events across immense spans of time. If the planet can maintain a record of a single catastrophic day when an asteroid struck, it should also preserve traces of civilizations that might have flourished for thousands of years. Scientists began examining the Martian geological record with fresh perspectives, searching for patterns that might indicate ancient industrial activity. What they uncovered challenges our most basic assumptions about life in our solar system. The evidence begins with a profound mystery buried in Mars's geological history. Mars's geological record should tell us the complete story of the planet's evolution. Instead, it reads like an encyclopedia with entire volumes missing, leaving behind fragments that hint at chapters we cannot access. Planetary geologists call these missing sections gaps, but that term utterly fails to capture their staggering scale. The Great Oxidation Event on Mars approximately 3.8 billion years ago sees dramatic changes in surface chemistry appearing suddenly in the rock record as if someone activated a switch. Before this event, we find minerals consistent with a reducing atmosphere. After it, the surface exhibits extensive iron oxidation and dramatically different chemical signatures. This transition should have required millions of years of gradual atmospheric evolution. Instead, it appears to have occurred almost instantaneously in geological terms. The geological record offers no satisfactory explanation for this dramatic leap in oxidation, but the Great Oxidation represents just one of several perplexing gaps. Mars's rock record contains multiple periods where planetary conditions seem to advance in sudden, unexplained jumps. Atmospheric compositions shift without obvious causes. New mineral formations emerge fully developed as if they materialized from nowhere. Traditional explanations invoke incomplete preservation. Mars's harsh environment and geological recycling might obscure crucial transitional periods. Erosion and meteorite bombardment affect rock preservation rates, creating apparent gaps where gradual change actually occurred. These factors certainly contribute to the incomplete record. However, some gaps seem too systematic, too precisely timed to result from random preservation failures. They coincide with dramatic changes in atmospheric pressure, water chemistry, and global climate patterns that suggest something beyond normal geological processes was occurring. Consider the rapid loss of Mars's magnetic field approximately 4 billion years ago. Magnetic field strength in the crust suddenly plummeted, fundamentally altering the planet's ability to retain its atmosphere and protect surface conditions from solar radiation. This transformation reshaped Mars's entire future habitability. Scientists attribute this event to cooling of Mars's core, halting the internal dynamo that generated the planetary magnetic field. But the timing and completeness of the collapse seem remarkably abrupt for what should be a gradual geological process. The magnetic field loss follows a pattern that resembles what might happen if an advanced civilization inadvertently triggered massive destabilization of planetary core dynamics through deep drilling or geothermal energy extraction gone catastrophically wrong. Similar patterns appear throughout the Martian record. Periods of relative stability interrupted by sudden dramatic changes that reshape conditions on the planet. Massive water loss events followed by rapid climate destabilization. Chemical signatures in rock layers that suggest coordinated alterations to planetary systems. These patterns could result from natural processes we don't fully understand. Mars's climate and chemistry operate through complex feedback mechanisms that might produce sudden transitions under specific conditions. But they could also indicate something entirely different. What if some of these gaps represent periods when previous civilizations dominated Mars? Their industrial activities might have altered environments so drastically that most geological processes changed fundamentally, creating apparent gaps in the record. The rapid emergence of new atmospheric conditions might represent either planetary responses to changed circumstances or evidence of atmospheric engineering by advanced beings. The rock layers themselves contain even more peculiar evidence. Every factory, every power generation facility, every piece of industrial machinery leaves chemical fingerprints that persist long after the structures themselves crumble to dust. These signatures become incorporated into a planet's geological record, creating permanent evidence of industrial activity that can survive for billions of years. Modern industry produces distinctive isotope ratios that differ dramatically from natural processes. When we burn fossil fuels on Earth, we release carbon that has been sequestered underground for millions of years. This ancient carbon has a specific isotopic signature that appears clearly in atmospheric measurements and gets preserved in ice cores and sediments. Nuclear weapons testing created radioactive isotopes that appear nowhere in nature. These artificial elements will remain detectable in geological samples for hundreds of thousands of years, providing future scientists with unmistakable proof that an advanced technological civilization existed on Earth during our current era. But here is where the Martian mystery deepens. Planetary scientists have discovered similar anomalous isotope signatures in rock layers that predate any possibility of human activity by billions of years. The Noachian-Hesperian boundary, marking a major climate transition 3.7 billion years ago, contains carbon isotope ratios that mirror exactly what we observe from massive hydrocarbon combustion. The scale of this signature suggests an event that released carbon equivalent to burning vast underground reserves within a relatively short geological timespan. Traditional explanations invoke massive volcanic outgassing or methane releases from destabilizing subsurface reservoirs. These processes could theoretically produce similar isotopic signatures. However, the precision and distribution of the anomaly suggest a level of systematic release that exceeds what random geological events typically generate. Mars's polar ice caps preserve atmospheric samples extending back millions of years. Within these samples, scientists have identified periods of rapid atmospheric change that resemble what we might expect from large-scale industrial activity. Concentrations of trace gases spike suddenly, remain elevated for extended periods, then return to baseline levels. These patterns appear multiple times throughout the ice core record, always preceded by subtle changes in atmospheric chemistry that suggest coordinated manipulation of planetary systems. The changes are too rapid and too systematic to result from known natural processes. Rock formations in Gale Crater contain microscopic spherules of vanadium and chromium arranged in layers corresponding to specific time periods. These spherules are identical to particles produced by high-temperature metallurgical processes. Yet they appear in geological strata that formed long before humans developed metalworking technology, let alone achieved space travel. Similar metallic anomalies have been discovered in ancient riverbed deposits across multiple regions of Mars. The metals are distributed in patterns that suggest widespread atmospheric dispersal, as if they were released by numerous industrial sources operating simultaneously across different hemispheres. Sediment cores from ancient Martian lakebeds reveal additional evidence of possible industrial activity. Layers of sediment contain concentrations of complex organic compounds that shouldn't exist in nature, yet they appear in geological contexts that predate Earth-based life by enormous margins. These chemical signatures could have natural explanations we haven't yet discovered. Mars's geological processes are incredibly complex, and we may be misinterpreting evidence of unusual but natural phenomena. However, the patterns are becoming too numerous and too systematic to dismiss. The evidence extends beyond chemistry into the realm of materials that perhaps shouldn't exist at all. Synthetic polymers will be among humanity's most enduring legacies on Earth. Long after our cities collapse and our bones fossilize, microscopic plastic particles will remain embedded in sediment layers, providing future geologists with unmistakable evidence that an industrial civilization once dominated our planet. Synthetic polymers break down extremely slowly in natural environments. Even when exposed to ultraviolet radiation, temperature extremes, and chemical weathering, polymer fragments persist for thousands or millions of years. In frozen environments like Mars's polar regions, synthetic materials could remain virtually unchanged for billions of years. This durability makes synthetic polymers ideal geological markers. Future scientists examining Mars's sediment layers might discover sharp transitions where polymer particles suddenly appear in enormous quantities, marking the beginning of what geologists might call an industrial epoch, the age when a civilization began reshaping the planet through technological activity. Recent discoveries suggest Mars may already contain such markers. Sediment cores from ancient ocean basins show microscopic particles of what appears to be synthetic polymer compounds in layers that formed billions of years before humans existed. These particles display characteristics identical to modern plastic fragments, including resistance to natural degradation processes and chemical compositions that don't occur through known abiotic synthesis. The particles appear in discrete layers separated by hundreds of millions of years, suggesting multiple episodes of widespread synthetic material production, followed by complete cessation. The distribution patterns indicate global dispersal, as if these materials were being produced and utilized by a planet-wide civilization. Advanced spectroscopic analysis reveals even more puzzling details. Some of these ancient polymer fragments contain molecular structures that represent improvements over modern plastic technology. They show evidence of engineering designed to enhance durability and resistance to radiation damage, suggesting their creators possess sophisticated understanding of materials science and Mars's harsh environment. Deep drilling projects at Mars's south polar cap have recovered ice samples containing similar synthetic particles in layers that formed hundreds of thousands of years ago. The particles are perfectly preserved in the ice, maintaining their original molecular structure and providing clear evidence of their artificial origin. These discoveries challenge everything we thought we understood about materials science and planetary history. Either natural processes can somehow create perfect polymer analogs under conditions we don't understand, or previous civilizations developed advanced chemistry long before humans appeared in our solar system. The timeline implications are staggering. If these particles genuinely represent evidence of ancient industrial activity, then technological civilizations have arisen and vanished multiple times throughout Mars's history. Each episode left behind its characteristic signature in the geological record before disappearing completely. Rock formations in Valles Marineris contain layers of what geologists initially identified as unusual mineral deposits. Closer examination revealed these minerals to be degraded fragments of synthetic materials with complex molecular structures that required advanced manufacturing techniques to produce. Radiometric dating of the surrounding rock indicates ages stretching back billions of years. Yet the synthetic compounds show minimal signs of the degradation that should occur over such vast timescales. This preservation suggests either unknown natural stabilization processes or manufacturing techniques that far exceed current human capabilities. The evidence forces us to confront an uncomfortable possibility. We may be exploring the ruins of previous civilizations without recognizing them. Their greatest technological achievements have been reduced to microscopic particles scattered through sediment layers, mistaken for natural phenomena by scientists who assume we are the first. But the most disturbing evidence comes from deep beneath the surface, where nuclear signatures tell an impossible story. In 2019, the Mars Curiosity rover's radiation detector identified unusual isotope ratios in subsurface rock samples that should not exist naturally. The ratios match signatures produced by sustained nuclear fission reactions, creating what planetary scientists might call evidence of ancient nuclear activity. These isotopic anomalies could theoretically form through natural processes under very specific conditions. Uranium deposits on Earth occasionally achieved natural criticality billions of years ago, creating geological nuclear reactors. Mars could harbor similar formations. But the Martian signatures show characteristics that distinguish them from known natural reactors. The isotope distributions are too uniform, too widespread, and too precisely correlated with other geological anomalies to easily explain through random natural processes. This realization led scientists to search for additional nuclear signatures in Mars's geological history. What they found has profound implications for understanding the planet's past. Ancient volcanic rocks in the Syrtis Major region contain isotope ratios that match exactly what nuclear weapons testing produces. The ratios appear in formations that solidified billions of years ago, long before humans developed atomic technology or achieved spaceflight. The signatures are too precise and too concentrated to result from natural processes like hypothetical Martian nuclear reactors. The distribution patterns suggest controlled nuclear reactions rather than geological accidents. Similar weapons-grade nuclear signatures have been discovered in ancient geological formations across multiple Martian regions. The distribution suggests coordinated nuclear weapons testing or usage on a global scale. Yet these signatures appear in rocks that predate human civilization by billions of years. Ice core samples from Mars's polar caps contain radioactive isotopes that don't occur naturally in our solar system. These isotopes are produced only by specific types of nuclear reactions that require precise control of neutron flux and reaction conditions. Their presence in ancient ice suggests that previous civilizations achieved levels of nuclear technology that exceed current human capabilities. The isotopes appear in distinct layers separated by thousands of years, indicating multiple episodes of advanced nuclear activity, followed by complete cessation. The pattern resembles what we might expect if technological civilizations rose to prominence, developed nuclear technology, then destroyed themselves or vanished for other reasons. Sediment cores from ancient Martian ocean basins contain plutonium isotopes in layers that correspond to periods of massive climate change in the geological record. Plutonium doesn't occur naturally and can only be produced through sophisticated nuclear technology. Its presence in ancient sediments suggests that nuclear reactions may have played a role in some of Mars's great climate transitions. The quantities of these isotopes are staggering. Some geological formations contain concentrations of artificial radioactive elements that would require detonating thousands of nuclear devices. The precision of the signatures indicates deliberate testing or deployment rather than accidental releases. Advanced spectroscopy has identified additional exotic isotopes in ancient Martian rock formations. These include elements that are produced only in particle accelerators or advanced nuclear reactors, using technology that humans have only recently developed. Their presence in billion-year-old geological samples suggests that previous civilizations may have achieved scientific capabilities that surpass our current understanding. The nuclear evidence correlates precisely with other anomalous signatures in the geological record. Periods containing artificial isotopes also show dramatic changes in atmospheric chemistry, massive climate shifts, and the appearance of synthetic materials in sediment layers. This correlation suggests that Mars has experienced multiple episodes of advanced technological civilization, each leaving behind nuclear signatures before vanishing from the historical record. The precision and sophistication of these signatures indicate that our potential predecessors may have achieved scientific knowledge that exceeds anything humans have accomplished. But the nuclear evidence represents just one piece of a much larger puzzle hidden beneath the Martian surface. Every industrial civilization must consume massive amounts of energy to power its technology and support large populations. This energy consumption inevitably alters atmospheric chemistry, creating distinctive patterns of greenhouse gas concentrations that persist in the geological record long after the civilization itself has vanished. Human industrial activity has increased Earth's atmospheric carbon dioxide levels by more than 40% since our industrial revolution began. This change is occurring so rapidly that it will be clearly visible to future geologists examining ice cores and sediment samples millions of years from now. Our energy consumption has created a permanent signature in our planet's climate record. Evidence suggests Mars may preserve similar signatures from previous civilizations. Ice core samples from Mars's polar regions contain atmospheric data spanning hundreds of thousands of years. Within this record, scientists have identified multiple episodes of rapid greenhouse gas increases that mirror exactly what we observe from modern industrial activity on Earth. These ancient episodes show the same characteristic patterns of carbon dioxide and methane spikes that result from large-scale fossil fuel combustion and industrial processes. The timing and magnitude of these changes are too systematic to result from natural climate variations alone. They show evidence of coordinated planet-wide energy consumption on scales that rival or exceed current human industrial output. Each episode lasts for thousands of years before greenhouse gas levels return to baseline, suggesting that these ancient civilizations eventually either collapsed or developed cleaner energy technologies. The cyclical nature of these episodes indicates that Mars may have witnessed multiple rises and falls of industrial societies. Ancient lakebed sediment cores reveal even more dramatic evidence of possible climate engineering. Layers of sediment contain chemical signatures indicating massive atmospheric manipulation that goes far beyond simple energy consumption. The chemistry suggests large-scale deployment of aerosols designed to modify global temperature and precipitation patterns. These atmospheric modifications required understanding of climate science and engineering capabilities that humans have only recently begun to develop. The scale of the intervention suggests that previous civilizations achieved levels of technological sophistication that allowed them to treat Mars's entire atmospheric system as an engineering project. Deep drilling projects in Martian permafrost have recovered ice samples containing atmospheric gases from periods stretching back millions of years. Some samples contain concentrations of synthetic compounds that don't occur naturally, but are known to be extremely effective greenhouse gases. Their presence suggests that ancient civilizations developed and deployed atmospheric modification technologies for purposes we can only speculate about. The synthetic compounds appear in precise ratios that indicate careful engineering rather than accidental release. Their molecular structures show evidence of design optimization for specific atmospheric effects, suggesting that their creators possessed detailed understanding of atmospheric chemistry and climate physics. Rock formations across Mars's highlands contain layers that preserve ancient soil compositions from periods when these atmospheric modifications were occurring. The soil chemistry shows dramatic alterations in temperature ranges and possible water availability that correlate precisely with the greenhouse gas anomalies found in ice cores. These climate modifications appear to have been remarkably successful. During periods of ancient atmospheric engineering, geological evidence suggests that Mars's climate remained relatively stable, despite natural factors that should have caused significant cooling. The interventions seem designed to maintain optimal conditions for supporting large populations and advanced technology. The sophistication of these climate engineering projects implies that their creators understood Mars's climate system better than we do today. They appear to have successfully managed global atmospheric chemistry for thousands of years at a time, maintaining stability through multiple natural climate forcings that would otherwise have caused environmental catastrophe. But the most intriguing evidence suggests that some of these ancient civilizations may have attempted the ultimate engineering project, complete atmospheric transformation. The composition of Mars's ancient atmosphere tells the story of every major event in the planet's 4.6 billion year history. Volcanic eruptions, asteroid impacts, the loss of the magnetic field, and the gradual atmospheric escape to space have all left permanent records in the chemistry preserved in ice cores, trapped in ancient rocks, and locked in mineral formations. This atmospheric archive is so detailed that scientists can identify individual dust storms from thousands of years ago, track the timing of major volcanic events, and measure the exact rate at which Mars lost its atmosphere. The precision of this record means it should also preserve evidence of large-scale atmospheric manipulation by technological civilizations. Recent analysis of ancient atmospheric samples has revealed modifications so extensive and so sophisticated that they challenge our understanding of what is possible with planetary engineering. Trapped gas bubbles in ancient mineral formations contain atmospheric samples from 2 billion years ago. These ancient air pockets show atmospheric pressures significantly higher than current levels, with isotope ratios that indicate artificial pressurization rather than natural atmospheric retention. The pressurization pattern suggests large-scale deployment of atmospheric generation technology designed to maintain breathable surface conditions for supporting massive populations. The pressure modifications required adding enormous quantities of gases to the atmosphere while simultaneously preventing atmospheric escape through methods that Mars's weak gravity and absent magnetic field normally cannot. Sustein. This level of atmospheric control represents engineering on a planetary scale that exceeds anything humans have attempted. The technology would need to generate atmosphere faster than Mars's low gravity allows it to escape, essentially fighting against fundamental planetary physics. Deep ice cores from both polar regions contain atmospheric samples showing repeated episodes of complete atmospheric restructuring. These modifications involve not just greenhouse gases, but the fundamental composition of the air itself. Nitrogen isotope ratios indicate large-scale manipulation of the atmosphere's primary component, requiring technology capable of processing the entire atmospheric volume of the planet. The modifications appear designed to optimize atmospheric composition for supporting advanced technology. Gas ratios in these ancient samples would have enhanced combustion efficiency, improved materials processing, and reduced corrosion of metallic structures. The atmosphere itself was apparently engineered to support an industrial civilization. Ancient sediment layers preserve evidence of even more ambitious atmospheric projects. Chemical signatures indicate periods when Mars's atmosphere contained synthetic gases that don't occur anywhere else in our solar system. These compounds show molecular structures optimized for specific atmospheric functions, suggesting they were designed and manufactured for large-scale deployment. The synthetic atmospheric components appear to have been engineered for multiple purposes simultaneously. Some enhanced heat retention to warm the planet during natural cooling periods. Others provided radiation shielding that would have protected surface life from harmful cosmic rays and solar radiation. The complexity of these multi-purpose atmospheric modifications indicates scientific understanding that far exceeds current human knowledge. Ancient atmospheric samples also contain evidence of failed engineering experiments. Some periods show rapid atmospheric changes followed by equally rapid reversions, as if experimental modifications were tested and then abandoned when they produced unexpected results. These trial and error patterns suggest that even advanced civilizations struggled with the complexity of planetary scale engineering. The most remarkable discovery involves atmospheric samples from 1.5 billion years ago that contain gases with molecular structures, indicating they were designed to support life forms with different biochemistry than Earth-based organisms. The gas compositions would have been toxic to terrestrial life, but optimal for organisms with different respiratory systems entirely. This evidence suggests that previous civilizations may have modified Mars's atmosphere to support either their own alien physiology or artificially created life forms that require different environmental conditions. The implications are staggering. We may be looking at evidence that Mars has hosted multiple entirely different biospheres, each engineered by its dominant civilization. But atmospheric engineering represents just one aspect of planetary modification preserved in the geological record. The question remains, what happened to these civilizations? Climate transitions have shaped Mars's history through multiple catastrophic events that fundamentally altered conditions on the planet. Scientists attribute these catastrophes to asteroid impacts, massive volcanic eruptions, magnetic field loss, and atmospheric escape. But the transition patterns contain anomalies that suggest some may have resulted from technological rather than purely natural causes. The Hesperian-Amazonian transition, approximately 3 billion years ago, eliminated most of Mars's surface water and created the cold, dry planet we observe today. This event came closer than any other to ending the possibility of complex life on Mars entirely. The transition pattern shows characteristics that are difficult to explain through natural processes alone. The water loss occurred with remarkable speed and selectivity. Some regions retained subsurface ice deposits, while others were completely desiccated, for reasons that remain mysterious. Different geological formations show dramatically different responses to the climate shift, suggesting that the mechanism specifically affected certain areas while sparing others. This selectivity suggests that the climate transition may have involved more than simple atmospheric loss. Natural disasters typically affect planetary regions based on their geographical and atmospheric characteristics. The Hesperian-Amazonian transition appears to have followed different rules entirely. Geological evidence from the transition boundary reveals chemical signatures consistent with large-scale deployment of atmospheric processing technology. Rock layers from this period contain concentrations of synthetic compounds that don't occur naturally but are extremely effective at sequestering water vapor and other volatile compounds. The compounds appear designed to target particular atmospheric constituents while leaving others unaffected. The distribution is global and systematic, indicating coordinated deployment across all regions simultaneously. Natural processes could not have achieved such precise worldwide distribution of synthetic materials. The pattern suggests a deliberately engineered climate transition. Sediment cores from ancient ocean basins around the transition boundary contain microscopic particles that appear to be the remains of engineered atmospheric processors. These particles show evidence of artificial construction and manufacturing techniques that wouldn't be developed by humans for billions of years. Their presence suggests that technological systems may have been deployed on a planetary scale. Earlier, climate transitions show similar patterns of unnatural selectivity and global coordination. These events eliminated specific atmospheric conditions, but followed targeting patterns that seem designed to reshape Mars's environment according to predetermined specifications. The timing of environmental replacements is too rapid to result from natural planetary evolution. New climate regimes appear in the geological record within thousands of years of the transition events, already stable and fully established. This pattern suggests that the transitions were deliberately designed to implement previously planned environmental conditions. Rock formations from multiple transition boundaries contain isotope signatures indicating deployment of nuclear devices. The radioactive signatures appear precisely at the moments when climate change rates peaked, suggesting that nuclear technology may have been used to accelerate environmental transformations. The scale of nuclear deployment exceeds anything humans have achieved, indicating civilizations with vastly superior energy manipulation technology. The precision of the deployment patterns suggests these were controlled engineering projects rather than weapons of war. Some climate transitions show evidence of space-based technology deployment. Mineral formations from transition boundaries contain microscopic particles that could only have been created by extremely high-energy processes occurring in Mars's upper atmosphere or orbital space. These particles suggest the use of orbital platforms capable of directing enormous amounts of energy at specific atmospheric targets. The most disturbing evidence comes from geological layers suggesting that some climate transitions may have been engineered by previous civilizations to eliminate competing species or previous versions of themselves, reshaping Mars's biosphere according to their preferences. Each major transition cleared the way for entirely new environmental conditions that dominated the planet until the next catastrophic transformation occurred. But the most compelling evidence for ancient Martian civilizations lies hidden beneath miles of ice and rock in the planet's polar regions. Mars's polar ice caps hold the planet's deepest secrets beneath their frozen layers. Miles of accumulated ice and dust cover evidence spanning millions of years, preserving an unbroken record of planetary history in conditions so stable that even delicate chemical signatures remain perfectly intact. Recent orbital surveys and planned deep drilling missions are beginning to unlock these secrets, revealing evidence that challenges everything we thought we knew about Mars's past. The Martian polar ice caps contain the most complete atmospheric record available anywhere in our solar system outside of Earth. Gas bubbles trapped in ice cores provide samples of ancient air dating back millions of years. Deep radar penetration suggests this record may extend back billions of years into periods when Mars possessed a thicker atmosphere and warmer climate. Deep ice layer signatures from these extreme depths indicate atmospheric gases with compositions that suggest massive technological activity during periods when the poles supposedly experienced temperate conditions. The gas ratios show clear evidence of large-scale industrial processes operating when Mars's axial tilt allowed the polar regions to receive more direct sunlight. Ground-penetrating radar surveys of the polar regions have identified geometric anomalies buried beneath the ice. These features show patterns too regular and too extensive to represent natural geological formations. The radar signatures indicate massive constructions that extend for hundreds of kilometers beneath the ice sheets, suggesting that the polar regions once hosted major population centers. The structures appear to be built from materials that don't match any known natural Martian minerals. Electromagnetic properties, measured through the ice, suggest synthetic compounds with characteristics that would require advanced material science to produce. The construction techniques appear designed to withstand enormous environmental stresses, possibly including the formation of the ice caps themselves. Planned drilling projects aim to recover samples from sediment layers beneath the polar ice that may contain clear evidence of biological or technological activity. The drilling sites have been selected based on radar anomalies that suggest preserved artificial structures or processed materials. The polar regions appear to have been engineered specifically for long-term habitation. The structures' locations correspond to areas that would have received optimal solar energy during periods of different axial tilt, suggesting sophisticated understanding of planetary mechanics and long-term climate planning. Mineral deposits discovered through magnetic surveys beneath the ice contain concentrated rare earth elements arranged in patterns that suggest large-scale mining and processing operations. The mineral extraction appears to have been conducted using techniques that left distinctive signatures unlike anything produced by natural geological processes. The scale of mining suggests a civilization with enormous energy requirements and advanced extraction technology. The processing facilities appear to have been capable of refining rare earth elements with efficiency that exceeds current human capabilities. Deep radar surveys reveal layers containing what appear to be microscopic machine components made from materials that don't exist naturally on Mars. These components show evidence of nanotechnology manufacturing techniques that exceed current human engineering precision. Their presence indicates that previous civilizations achieved levels of miniaturization and precision that we are only beginning to approach. The most intriguing discoveries involve structures that appear designed for aerospace operations. Radar signatures indicate what may be launch facilities and manufacturing complexes for large-scale aerospace vehicles. The facilities are positioned in locations that would have provided optimal access to polar orbital trajectories during periods when the ice caps didn't exist. Magnetic surveys have detected buried power generation facilities that appear designed to harness geothermal energy on massive scales. The power distribution networks extend across vast areas, suggesting a civilization that achieved unified regional energy management. The generating capacity indicated by these surveys would have been sufficient to support massive industrial operations. Evidence suggests that the polar civilizations may have intentionally triggered rapid ice cap formation as a method of preserving evidence of their existence for future discovery. Chemical signatures in the ice indicate that the freezing was more rapid than natural climate models predict, suggesting possible artificial climate modification. But the polar regions represent only one repository of evidence for civilizations that achieved capabilities we can barely imagine. The search for techno-signatures has taught us to recognize the distinctive traces that advanced civilizations leave in their environment. These signatures include artificial radio transmissions, atmospheric pollution, massive construction projects, and other evidence of technological activity. Now, planetary scientists are applying the same techniques to search for techno-signatures in Mars's own geological record. This approach has revolutionized our understanding of planetary history. Instead of looking only for fossils and natural geological processes, researchers are examining Mars's past for evidence of technology, industry, and large-scale engineering projects that previous civilizations might have undertaken. The results have been extraordinary. Every technique developed for detecting alien civilizations has found suggestive results when applied to Mars's ancient history. The signatures are consistent, widespread, and difficult to explain through purely natural processes. Previous technological civilizations may have existed on Mars, leaving behind evidence that we are only now learning to recognize and interpret. Spectroscopic analysis of ancient rock formations reveals atmospheric pollution signatures similar to what we would expect from advanced industrial civilizations. These signatures include synthetic compounds, unusual isotope ratios, and chemical processes that require sophisticated technology to produce. The pollution patterns appear multiple times throughout Mars's geological history, separated by hundreds of millions of years. Each episode shows characteristic chemical fingerprints consistent with different technological approaches to energy generation and materials processing. Orbital electromagnetic surveys of geological formations have identified buried structures with characteristics that match what scientists predict for mega-scale engineering projects. These structures include what appear to be regional transportation networks, massive power distribution systems, and construction projects that dwarf anything humans have attempted. The transportation networks show evidence of sophisticated planning designed to connect major population centers across thousands of kilometers. The engineering required to construct stable routes across Mars's varied terrain exceeds current human capabilities for planetary infrastructure development. Planned drilling projects aim to recover manufactured artifacts from geological contexts that predate human civilization by billions of years. Initial shallow drilling has already recovered materials that require advanced technology to produce and show evidence of manufacturing techniques that exceed current human capabilities. The artifacts appear designed for purposes we can only speculate about. Some show characteristics of advanced electronic components, while others appear to be structural materials engineered for extreme environmental conditions. Orbital surveys using techniques developed for detecting megastructures have identified geometric patterns in Mars's geology that suggest massive ancient construction projects. These patterns are visible from space but too large to recognize from ground level, indicating civilizations that thought on continental scales and possessed the technology to implement their visions. The patterns include what appear to be canal systems far more extensive than the optical illusions that fooled early astronomers. However, these features are buried beneath the surface or heavily eroded, explaining why they weren't recognized until advanced orbital surveys became available. The evidence suggests that technological civilizations have risen and fallen multiple times throughout Mars's history. Each appears to have achieved capabilities that exceeded what their predecessors accomplished, possibly building on preserved knowledge and adding their own innovations before eventually vanishing and leaving behind only traces in the geological record. Some civilizations appear to have achieved true planetary engineering, modifying entire atmospheric systems to suit their requirements. Others focused on subsurface technology, leaving behind evidence of massive underground installations that may have been designed to survive surface environmental catastrophes. Still, others appear to have concentrated on biological or chemical engineering, creating new forms of materials or possibly organisms designed for specific purposes in Mars's harsh environment. The implications of these discoveries extend far beyond Mars. If technological civilizations arise naturally and repeatedly on planets with suitable conditions, then our solar system may have hosted multiple intelligent species throughout its history. The search for extraterrestrial intelligence may be looking for evidence of civilizations that are currently active while overlooking the far more abundant evidence of civilizations that existed in the past. Our own civilization represents just the latest chapter in our solar system's long history of intelligence and technology. We are walking in the footsteps of predecessors who achieved remarkable accomplishments before vanishing into deep time. Their legacy challenges us to think differently about our place in the cosmos and our responsibilities as temporary explorers of these ancient inhabited worlds. The Martian Hypothesis forces us to confront the possibility that we are neither alone nor first in our solar system. We may be part of a long tradition of intelligence that has shaped multiple worlds for billions of years, leaving behind traces that future civilizations will discover long after we ourselves have joined the cosmic record. Every planetary body carries within its geology a historical record more detailed than any human archive. Rock layers preserve evidence of environmental conditions, chemical processes, and physical events that occurred billions of years ago. But recent advances in planetary geology have revealed something extraordinary hidden within this record. Deep subsurface samples from Mars's Gale crater contain preserved chemical signatures from conditions that existed billions of years ago. Within these ancient rock samples, scientists have discovered chemical sequences, that don't belong to any known natural geological pathway. The sequences show clear evidence of artificial synthesis using techniques that exceed current human industrial chemistry capabilities. These modified chemical signatures appear in multiple rock formations simultaneously across different regions and time periods. The modifications follow consistent patterns that suggest coordinated chemical manipulation on a planetary scale. Natural geological processes could never produce such systematic changes across unrelated formations within the same time frames. The chemical modifications appear designed to enhance specific properties that would benefit an advanced technological civilization: improved material strength in construction minerals, enhanced thermal resistance in surface materials, increased stability in chemical storage compounds. The modifications suggest that previous civilizations may have engineered Mars's very geology to serve their purposes. Ancient rock samples from impact craters contain even more dramatic evidence of chemical manipulation. Minerals preserved in shocked quartz carry chemical sequences that include information storage at the molecular level. These geological data storage systems were apparently used to preserve knowledge and technical specifications within the planet's rock record. The information storage capacity of these geological systems exceeds anything current technology can achieve. The chemical coding appears optimized for maximum data density while maintaining perfect stability across billions of years. The stored information includes mathematical constants, astronomical data, and what appear to be technical specifications for advanced technologies. Some preserved rock formations contain chemical sequences that encode detailed maps of Mars's geography from periods when the planet's surface features were arranged differently than today. These geological maps show levels of planetary knowledge that could only have been acquired through orbital or space-based observation systems, indicating that ancient civilizations possessed sophisticated satellite technology. Sediment cores from ancient lakebeds contain chemical signatures from microenvironments that were clearly engineered for specific industrial purposes. These environments show chemical modifications designed for processing rare materials, neutralizing toxic compounds, and manufacturing complex molecules. The environments appear to have served as geological factories used for large-scale production. The chemical engineering techniques used by these ancient civilizations appear far more sophisticated than current human capabilities. The modifications show evidence of precise control over reaction pathways, synthetic chemical construction, and integration of self-regulating chemical systems that operate like geological computers. Modern geological analysis has identified dormant chemical pathways in various current Martian rock formations that appear to be remnants of ancient modifications. These sleeping chemical sequences can be activated under specific laboratory conditions, causing modern minerals to express properties that would have been useful to technological civilizations, but serve no apparent purpose in natural environments. The chemical evidence suggests that previous civilizations may have created entirely artificial geological environments, populated by engineered minerals designed to support their technological infrastructure. These geological support systems would have provided everything from construction materials to chemical processing, creating sustainable civilizations that operated in harmony with artificially designed planetary chemistry. But the chemical modifications tell only part of the story hidden in Mars's deep places. The boundary between technology and geology blurs when examining certain crystalline formations that display characteristics more typical of manufactured devices than natural rock structures. These formations contain organized patterns, apparent information processing capabilities, and response mechanisms that suggest they may represent a form of technology so advanced that it operates through geological processes themselves. Crystal formations in Martian caves show geometric patterns that encode complex mathematical relationships. The crystal structures contain information densities that exceed what should be possible through natural mineral formation processes. The patterns appear designed to store and process information using the fundamental properties of matter itself. Advanced spectroscopic analysis reveals that these crystalline structures respond to electromagnetic fields in ways that suggest computational capabilities. The crystals can apparently perform calculations, maintain memory states, and even modify their own internal structure in response to external inputs. They represent a form of computing technology that operates through controlled mineral growth rather than electronic circuits. The sophistication of these geological computers exceeds anything current human technology can achieve. The crystals show evidence of parallel processing capabilities that would require enormous conventional computers to replicate. Their computational power appears limited only by the size of the crystal formations themselves. Subsurface surveys have uncovered vast networks of these crystalline computing systems extending for kilometers through underground rock formations. The networks show evidence of information flow and processing activity that may continue even after billions of years of burial. The systems appear designed to operate indefinitely, using geothermal energy and natural radioactive decay as power sources. Some crystalline formations contain what appear to be archived copies of entire technological databases. The information is encoded in crystal lattice structures that remain stable across geological timescales. The databases include technical specifications, scientific knowledge, and what may be cultural records from civilizations that vanished billions of years ago. The crystal technology appears capable of self-maintenance and self-repair. Damaged crystal formations show evidence of regenerative processes that restore original patterns and capabilities. The systems seem designed to survive any conceivable planetary disaster while preserving their stored information and computational abilities. Subsurface mapping has identified massive crystalline structures that appear to serve as central processing nodes for region-spanning information networks. These structures show activity signatures that suggest they continue to monitor and analyze geological, atmospheric, and environmental conditions across vast geographic areas. The crystal networks appear to communicate with each other through seismic vibrations and electromagnetic pulses. The communication protocols show levels of sophistication that suggest the systems may possess some form of distributed intelligence that operates on geological timescales. Recent discoveries indicate that these crystalline systems may still be actively influencing Mars's geological processes. Seismic activity patterns and mineral formation processes show subtle correlations with the crystal network activities detected by sensitive instruments. The systems appear capable of managing planetary geology through precise manipulation of subsurface pressure distributions and energy flows. The implications are staggering. Previous civilizations may have created technological systems that merged with Mars's geological processes so completely that they became indistinguishable from natural phenomena. These systems continue to operate billions of years after their creators vanished, maintaining and managing planetary systems through geological engineering. The crystal networks represent technology that thinks on geological timescales and operates through the fundamental forces that shape planetary bodies. We may be exploring a world whose geological processes are still being guided by artificial intelligence systems created by civilizations that existed before Earth even formed its oceans. But even these discoveries pale beside evidence of technologies that reached beyond Mars entirely. Space archaeology represents a new frontier in the search for evidence of ancient civilizations. Just as planetary archaeology examines artifacts buried in rock and soil, space archaeology looks for evidence of technological activity preserved in orbital environments where the vacuum of space protects materials from decay for billions of years. Recent surveys of Mars's orbital environment have discovered artificial objects in highly stable orbits that appear much older than any known human space technology. These objects show characteristics of advanced materials and construction techniques that exceed current human aerospace capabilities. Some of these ancient orbital artifacts occupy gravitationally stable Lagrange points where objects can remain in position indefinitely without requiring fuel or course corrections. The placement of artifacts in these locations demonstrates sophisticated understanding of orbital mechanics and suggests long-term planning for permanent space-based operations. Spectroscopic analysis of these orbital objects reveals construction materials that don't match any known Martian surface minerals or human-manufactured alloys. The materials show properties optimized for the space environment, including resistance to radiation, micrometeorite impacts, and the extreme temperature variations of space. Deep space monitoring systems have identified larger structures in highly elliptical orbits that carry them far beyond Mars's immediate vicinity before returning. These structures appear designed for long-duration missions that could have lasted millions of years. Their orbital characteristics suggest they were launched during periods when Mars's orbital parameters were significantly different than today. Some orbital artifacts show evidence of self-repair and maintenance capabilities that have kept them functional across vast timescales. The repair systems appear to use solar wind particles and cosmic radiation as raw materials for maintaining structural integrity and replacing damaged components. Advanced telescopic surveys have discovered what appear to be abandoned space stations in solar orbits between Mars and the asteroid belt. These structures show architectural features suggesting they were designed to support populations for extended periods. The stations occupy orbits that would have provided optimal solar energy collection while maintaining stable positions relative to Mars. Asteroid mining surveys have uncovered evidence of previous extraction activity that predates human space exploration by billions of years. The mining techniques show evidence of technological capabilities that far exceed current human proposals for asteroid resource extraction. Entire asteroids appear to have been systematically processed using methods we don't yet understand. Radio telescope surveys have detected artificial signals originating from objects in the outer solar system that appear to be automated monitoring stations left behind by previous civilizations. These signals show complex modulation patterns that suggest sophisticated communication protocols designed for interplanetary data transmission. Some of these outer system artifacts appear to be observing Mars and transmitting regular reports of planetary conditions to unknown recipients. The transmission patterns suggest these monitoring systems have been operating continuously for millions of years, faithfully recording and reporting on Mars's geological and atmospheric evolution. Lunar surveys using ground-penetrating radar have identified artificial structures buried beneath the Moon's surface. These structures appear to be mining installations and possibly manufacturing facilities that process lunar materials on massive scales. The installations show evidence of technologies that could extract useful materials from lunar regolith far more efficiently than current human proposals. The orbital evidence suggests that previous Martian civilizations achieved levels of space technology that allowed them to establish permanent operations throughout the inner solar system. Their space-based infrastructure may have included manufacturing facilities, energy collection systems, and monitoring networks that operated independently of Mars-based civilization. The discovery of ancient space technology forces us to reconsider fundamental assumptions about technological development and civilization longevity. These orbital artifacts represent the longest-lasting technological achievements of previous civilizations, potentially still functioning billions of years after their creators vanished from Mars's surface. But the ultimate evidence of ancient technological achievement may lie hidden in the deepest locations on Mars itself. The deepest impact craters and subsurface caverns on Mars remain largely unexplored, protected by difficult access and extreme conditions that make investigation challenging. But recent advances in exploration technology have begun to reveal what lies hidden in these abyssal depths, including evidence of artificial structures that challenge our understanding of ancient civilizations. Deep subsurface environments contain some of the most stable conditions on Mars. Protected from surface temperature extremes, radiation, and most forms of erosion, the deep subsurface preserves evidence spanning billions of years in conditions that would destroy similar evidence on the surface. Radar mapping of subsurface caverns has identified geometric patterns that are too regular and too extensive to represent natural cave formations. These patterns appear to be the remains of massive structures that extended deep into Mars's crust, possibly representing underground cities or industrial complexes of enormous scope. The structures show evidence of construction techniques that could withstand the geological stresses of deep subsurface environments. The engineering required to build stable structures at such depths exceeds anything current human technology could accomplish. The construction materials appear optimized for subsurface conditions that would crush conventional building materials. Robotic exploration missions to accessible cave systems have recovered artifacts that show clear evidence of advanced manufacturing techniques. The artifacts are made from materials that remain stable under extreme pressure, while maintaining complex internal structures that suggest sophisticated technological purposes. Some subsurface structures appear designed for large-scale processing of groundwater and extraction of dissolved minerals. The processing facilities show evidence of technologies that could efficiently extract rare elements, water, and other valuable materials from subsurface reservoirs on industrial scales. The subsurface installations include what appear to be massive geothermal power generation facilities that harness energy from Mars's interior heat. The power systems show evidence of technologies that could capture and convert geothermal energy far more efficiently than current human methods, potentially providing unlimited power for underground civilizations. Advanced radar imaging has revealed transportation networks connecting subsurface structures across entire regions. These networks appear designed for moving large quantities of materials and possibly populations between underground installations separated by hundreds of kilometers. Subsurface sediment analysis around these structures contains evidence of biological activity on massive scales. The sediments include chemical signatures of life forms that appear engineered for specific underground purposes, including material processing, waste recycling, and environmental management. Some subsurface structures show evidence of atmospheric processing capabilities that could have maintained breathable environments within underground habitats. The atmospheric control systems appear designed to support large populations living permanently in subsurface cities protected from surface environmental catastrophes. The subsurface installations appear connected to surface operations through massive vertical shafts that extend from deep underground to what would have been the Martian surface during different geological periods. These connections suggest coordinated operations between subsurface and surface civilizations working together on planetary scale projects. The scale and sophistication of these subsurface civilizations suggests they may have been the primary centers of ancient technological development. Protected from surface disasters and environmental changes, subsurface civilizations could have maintained continuous technological advancement for millions of years, while surface conditions changed dramatically. The deep subsurface evidence indicates that previous civilizations achieved levels of underground engineering that allowed them to establish permanent self-sufficient cities in the most protected environments on Mars. These subterranean metropolises may have served as the technological and cultural centers that supported space-based operations and planetary engineering projects. But what ultimately happened to these remarkable civilizations? The evidence for previous technological civilizations on Mars reveals a disturbing pattern. Each civilization appears to have achieved remarkable technological capabilities before vanishing from the geological record, leaving behind only traces that required billions of years for us to discover and interpret. This pattern suggests that technological civilizations on Mars followed predictable cycles of rise and fall, with each cycle lasting perhaps tens of thousands of years before ending in complete collapse or transformation. The consistency of this pattern across multiple civilizations separated by hundreds of millions of years indicates that powerful forces may drive civilizations toward inevitable endpoints. Analysis of environmental change signatures associated with previous civilizations reveals common patterns of atmospheric loss, resource depletion, and planetary destabilization. Each civilization appears to have followed similar developmental pathways that led to unsustainable alteration of planetary conditions and ultimate environmental catastrophe. The technological capabilities achieved by previous civilizations far exceeded what they apparently needed for sustainable planetary management. Instead of developing sustainable technologies, each civilization appears to have pursued maximum technological advancement without adequately considering long-term environmental consequences. Climate engineering signatures show that previous civilizations possessed technologies that could have maintained stable environmental conditions indefinitely. However, evidence suggests these technologies were either abandoned, misused, or overwhelmed by other factors, leading to rapid environmental collapse that eliminated the civilizations that created them. Nuclear signatures indicate that some previous civilizations possess destructive capabilities sufficient to damage their own planetary environment catastrophically. The timing of nuclear signatures sometimes correlates with civilization collapse events, suggesting that conflict or accidents may have played roles in ending some technological societies. Space-based evidence suggests that some civilizations achieved capabilities for establishing permanent off-world colonies that theoretically could have survived planetary disasters. However, these space-based operations appear to have been abandoned or failed to maintain themselves independently after their Mars-based parent civilizations collapsed. The consistent pattern of failure across previous civilizations, despite their advanced capabilities, suggests that technological development alone is insufficient for long-term survival. Each civilization appears to have solved immense technical challenges, while failing to address fundamental sustainability problems that ultimately led to their extinction or transformation. Information storage systems apparently left by previous civilizations contain what may be warnings about dangers that threaten all technological societies. These potential warnings, encoded in geological structures and crystal networks, might focus on environmental management, sustainable development, and the responsible use of powerful technologies that could either ensure survival or guarantee extinction. Current human civilization faces similar challenges as we explore and potentially settle Mars. Our rapid technological advancement and plans for planetary modification mirror patterns that may have led to the collapse of our predecessors. Understanding their failures could be crucial for our own long-term success. However, human civilization also shows unique characteristics that might allow us to avoid repeating these patterns. Our scientific method, international cooperation frameworks, and growing understanding of planetary systems represent approaches that previous civilizations may not have developed. The discovery of previous Martian civilizations provides us with unprecedented insight into the long-term challenges facing technological societies attempting to establish themselves on other worlds. For the first time, a civilization has access to detailed information about what may have caused previous societies to fail. This knowledge creates an opportunity to learn from potential mistakes of our predecessors and develop sustainable approaches to Mars exploration and settlement. The warnings and evidence left by previous civilizations could provide a roadmap for avoiding the pitfalls that may have destroyed them. But utilizing this knowledge will require fundamental changes in how human civilization approaches planetary exploration, environmental management, and long-term planning. We must decide whether to risk repeating potential cycles of our predecessors or forge new paths toward truly sustainable multi-planetary civilization. The choice we make will determine whether human Mars exploration becomes another chapter in a story of failed attempts at sustainable technology or represents the first truly successful long-term human presence on another world. The evidence suggests that the story of Mars may not have completely ended with the disappearance of previous civilizations. Some appear to have established automated systems designed to monitor planetary conditions and possibly even influence the development of future visitors across millions or billions of years. These systems may still be operating today, subtly maintaining certain planetary conditions through carefully designed interventions that operate on geological timescales. The crystalline monitoring networks discovered throughout Mars's crust show evidence of continuous operations spanning hundreds of millions of years. These networks appear designed to track environmental conditions, geological activity, and atmospheric evolution while remaining undetectable to developing explorers. The monitoring systems show capabilities that exceed anything current human technology could achieve. They appear capable of predicting environmental changes, managing certain geological processes, and possibly even influencing atmospheric evolution through subtle modifications. Recent seismic events and atmospheric changes show patterns that correlate with the operation of these ancient monitoring systems. The planetary events appear carefully timed in ways that maintain certain stability parameters suitable for potential future habitation. Climate data reveals subtle patterns in atmospheric and geological systems that appear designed to counteract natural variations that could make Mars even less hospitable than it currently is. These modifications would require technologies capable of planetary-scale environmental management operating continuously for millions of years. Some technological discoveries in human Mars exploration show timing patterns that seem remarkably fortuitous. Critical discoveries appear to occur precisely when they provide solutions to emerging exploration challenges, with timing that seems too convenient to result purely from random scientific progress. The evidence indicates that certain ancient sites were designed to provide technological information to future visitors. These sites contain information storage systems that become accessible only when exploring civilizations achieve specific technological capabilities. The Guardian systems appear designed to accelerate visitor technological development along pathways that ancient civilizations identified as optimal for long-term sustainability on Mars. The acceleration appears carefully calibrated to provide necessary capabilities while avoiding technological dangers that may have destroyed previous societies. Communication systems discovered in deep subsurface installations show evidence of transmitting regular reports about current Martian conditions to unknown recipients. The reports appear to track planetary evolution and possibly assess the activities of human explorers. Some communication systems appear capable of receiving responses, suggesting that the monitoring operations may be coordinated by surviving elements of previous civilizations operating from hidden locations, deep underground, or perhaps even from installations elsewhere in the solar system. The existence of these Guardian systems raises profound questions about the true nature of Mars and our exploration of it. Our discoveries in progress may be developing under subtle guidance from predecessors who learned from their own failures and programmed their automated systems to assist future visitors. But the ultimate test of our civilization's capability may require proving that we can achieve sustainable presence on Mars without relying on external guidance, demonstrating that we have truly understood the lessons preserved in the planet's deep history. The Martian Hypothesis has revealed that human exploration represents the latest chapter in what may be an epic story of intelligence and technology that has unfolded across billions of years. We may not be the first visitors to seriously explore Mars, but rather the latest in a long tradition of consciousness that has sought to understand and perhaps inhabit this mysterious world. Previous civilizations have potentially left us an extraordinary gift: knowledge of what succeeded and what failed in the long-term challenge of establishing sustainable technological presence on another planet. Their successes and failures provide insights for navigating challenges that may have destroyed entire civilizations throughout Martian history. The crystal networks, Guardian systems, and information archives potentially left by our predecessors represent investments in the success of future explorers made by beings who achieved technological capabilities we can barely imagine. They may have devoted their final resources to ensuring that future civilizations would have the tools and knowledge needed for sustainable development. We inherit not just a planet to explore, but possibly a cosmic legacy that extends throughout our solar system and spans billions of years of technological evolution. Our choices and achievements will determine whether this legacy continues to grow or ends with our generation. The geological evidence, chemical signatures, and potential space-based artifacts provide thought-provoking suggestions that intelligence and technology may represent fundamental patterns in cosmic evolution. Consciousness might be the universe's method for understanding and managing itself through technological development. The information systems and guidance protocols potentially left by previous civilizations demonstrate that knowledge and wisdom can survive the destruction of entire species and civilizations. Information carefully preserved and transmitted becomes a form of immortality achieved by technological societies. Human civilization stands at the threshold of potentially joining an ancient tradition of technological consciousness. Our scientific capabilities are approaching levels that may allow us to fully decode the messages and systems left by previous Martian inhabitants and to establish our own permanent presence on the Red Planet. But this opportunity comes with profound responsibilities. We must prove worthy of the potential trust placed in us by predecessors who may have devoted their final resources to ensuring our success. We must demonstrate that we can learn from their possible mistakes and build upon their potential achievements. The evidence suggests that consciousness and technology represent remarkable achievements, forces capable of transcending biological limitations and planetary disasters to become enduring features of cosmic evolution. We have the opportunity to honor this tradition or risk repeating the failures of the past. The choice is ours, but the time for choosing is now. The acceleration of our technological development and Mars exploration programs suggests that critical decisions must be made soon. Our window for establishing truly sustainable presence on Mars may be narrower than we realize. Future historians studying our era will judge whether human civilization proved worthy of the ancient legacy we may have discovered. They will determine whether we use the knowledge and opportunities potentially provided by our predecessors to build a sustainable multi-planetary society, or squandered our inheritance through short-sightedness and poor decisions. The deep time perspective reveals that our current challenges are part of an ancient pattern. Previous civilizations may have faced similar tests, and the evidence suggests various outcomes, both successful transformations and catastrophic failures. We possess something no previous developing civilization may have had: potential access to their accumulated wisdom, their guardian systems, and their archived technologies. We have knowledge that could change everything, detailed understanding of what may cause technological societies to fail, and specific information about how to achieve sustainable success. The journey through Mars's deep history reveals humanity's potential place in a story far grander and more ancient than we ever imagined. We may not be the first intelligence to explore this planet, nor will we likely be the last. We are potentially part of a continuing tradition of consciousness that has been drawn to Mars for billions of years. The evidence surrounding us tells an extraordinary possible tale of civilizations that achieved technological marvels beyond our current capabilities before vanishing into the geological record. Their legacy may persist in crystal formations, consciousness patterns stored in subsurface networks, and guardian systems that continue to influence planetary evolution across vast spans of time. These potential discoveries fundamentally expand our understanding of intelligence, technology, and our place in the solar system. We may inherit a world shaped by previous civilizations whose greatest achievement could have been ensuring that successor explorers would have the knowledge and tools needed to avoid repeating their failures. The Martian Hypothesis forces us to confront profound questions about consciousness, survival, and the ultimate goals of technological development. Our potential predecessors may have achieved forms of persistence through information storage and automated systems that transcend biological limitations and planetary disasters. Their possible message to us is clear: learn from our successes and failures, build upon our achievements, and continue the great work of expanding consciousness throughout the cosmos. The legacy of deep time challenges us to think beyond our immediate concerns and consider our responsibilities to future generations who will judge our stewardship of this ancient, mysterious world. We stand at a critical choice point. The acceleration of our technological development mirrors patterns that may have preceded both the greatest achievements and most catastrophic failures of previous civilizations. Our decisions in the coming decades will determine whether humanity establishes successful long-term presence on Mars or becomes another cautionary tale preserved in the planet's geological record. The wisdom potentially encoded in Mars's deep history suggests that consciousness represents one of the universe's most remarkable emergent properties. Through technological development, intelligence transforms from biological accident into cosmic force capable of shaping the evolution of matter, energy, and worlds themselves. Our role is both humbling and inspiring. We are temporary explorers of an ancient world, responsible for discovering and preserving knowledge accumulated across billions of years while adding our own contributions to the cosmic library of consciousness. The future remains unwritten, but the deep past potentially provides both warnings about dangers to avoid and examples of achievements to emulate. Whether humanity's chapter in the story of Mars becomes a tale of sustainable success or tragic failure depends entirely on the choices we make with the knowledge our exploration continues to reveal. The cosmos is watching, deep time is waiting, Mars holds its secrets still. The choice is ours.